Questa si sente di più forse, sì. Allora, volevo dire che grazie per essere qua. Fra pochissimi minuti noi cominciamo. Ecco, è arrivata Maryna Viazovska che è qui con noi. La ringraziamo moltissimo per essere stata disponibile. Come vedete, Maryna Viazovska è una donna molto giovane. Immaginavate, che ne so, una specie di non so, una persona magari anziana, una giovanissima donna che ha avuto il merito di essere insignita dalla Medaglia Fields di matematica, che è il riconoscimento più grande che possa essere dato a un matematico nella sua carriera a livello mondiale. È la seconda donna nella storia a ricevere questo premio. Viene dato ai matematici che abbiano meno di 40 anni. Mi hanno spiegato, io pensavo per incentivare i giovani agli studi, no, poi la vostra professoressa di alcuni di voi in vernizio mi ha spiegato che viene dato ai matematici di non più di 40 anni perché si considera che un matematico il massimo che può darlo lo dà entro quell'età, insomma. Comunque per noi è per noi un onore grandissimo. Per noi è un onore grandissimo ospitare la professoressa, docente all'Università di Losanna, girato un po' tutto il mondo. Spero che cogliate questa opportunità e che vi rendiate conto della grandezza di questa opportunità. Io non vi tormento più perché c'è già qualche minuto di ritardo. Buon pomeriggio e grazie ancora, Maryna.
Thank you very much for the introduction. So I'm ready to answer your questions. So, yes.
I wondered, why did you decide to work on the subject of sphere packing, and also when did you first come across it? And why did you choose to work specifically on the dimensions 8 and 24?
Yeah, so here maybe the answer is not very exciting. It's just I worked in this area of mathematics, of geometric optimization, and this was one of the big open questions, so questions everybody looked at. And the reason I started working on dimensions 8 and 24 is because there was really hope that these dimensions could be solved. It's like dimension 1 is trivial, 2 is boring, 3 is very difficult but already solved by Thomas Hales, and 4 seems like hopeless, 5, I don't know. I don't think that even you will live long enough so that we solve it in dimension 5, maybe in dimension 4. But then in dimensions 8 and 24, there was actually a paper by 2 American mathematicians, Henry Kohn and Noam Elkis, where they actually almost solved the problem. So they showed that if there is another packing which is denser than the E8 packing, it can be only like 1/1,000,000% denser, and similar result they had for dimensions 24. So here it was clear that it's like a low-hanging fruit, so that's why I came for it.
How did you come up with the idea of reasoning in other dimension beside the first 3, and how it's possible to work in dimensions above the third without seeing them, and can you somehow imagine them?
Yeah, so first maybe I want to say that it's not true, it's not that I came up with the idea of higher dimensions. It existed long time before me. And yeah, so this is actually a very interesting question. So first, how do we come up with the idea of higher dimensions? So here we do it by method of say mathematical abstraction. So we know what are dimensions 1, 2, and 3. We all can see them, feel them. We solve probably many problems about planimetry and stereometry at school. And now, as a mathematicians, what we observe that what is a dimension? That's like the number of coordinates of a point. And if you think abstractly, then nothing stops us from introducing other dimensions. And here maybe where like a magic happens, that many notions that we know from our three-dimensional life, they also generalize to higher dimensions, and they're still meaningful there. So, for example, as we think of a point in dimension 3, we can think of it as its 3 coordinates. And so, for example, point in dimension 4 is just 4 real coordinates. And then when we have these 4 real coordinates, or 1 point in 4-dimensional space, what we can do, we can take 2 points and measure distance between them. Or we can define what is a volume in 4-dimensional space, and what is the angle between, what are lines in multidimensional space, and what is the angle between lines. And all these concepts, they're still useful and they still make sense. And so how we actually, how we use them, why is it not just a waste of time to think about higher dimensions? It's because thinking of abstract notions geometrically, it's actually very useful to work with information. So whenever you have 4 meaningful numbers, one trick you could do, you could think, okay, so can I think about this information in geometric terms? And in many, many cases, this turns to be extremely useful. Maybe like the biggest successes are in physics, theoretical physics, but actually similar things work in other sciences as well. So whenever we have many numbers, we can think about, so what's the structure in these numbers? And then putting them into multidimensional structures is actually helpful and useful.
Are you going to look for the optimal solution for the other dimension as well? And will it make sense if you work at bigger and bigger dimensions?
Yes, of course, it would be interesting to solve all of them, probably impossible. So I'm not sure that I will be the person who solves the next dimension. As I say, maybe during our lifespan somebody will crack dimension 4, and who knows, maybe it will happen even fast. So here I have some hope, and I cannot say that I'm very actively working on it, but it's a problem which is on my radar. And then, like, one of my favorite problems in mathematics is working on packings in very high dimensions. For example, constructing new packings, or proving that they cannot be too dense, or proving that there exist configurations that are dense enough. So this is actually very, like, it's a big area of research, and I also work in there and plan to continue working because the number of questions is infinite. So it would be nice to answer some more of them.
When you started studying the mathematical problem of packing spheres, did you foresee the possibility of its applications in data transmission? Are there any other fields in which you findings could find application besides the transmission of messages? To your knowledge, are there real-life situations or applications that you find a solution by solving the problem of packing in other dimensions?
Yeah, so here maybe I have some bad news. So maybe one thing I should say that this idea of connection between sphere packing problem and codes transmission, it's not my idea. It existed actually a long time before I was born, or even my parents were born. So, and I think the person who first introduced this idea was Claude Shannon, and he did this at the actually during the Second World War, and then his results were published after the Second World War. And so this, I think, is a very beautiful idea, and it is used. And here maybe one a portion of bad news is that my result is not really applicable to the signal transmission, because I prove that something cannot be packed better, and what is useful for transmission is the recipe how to pack. So in this sense, it's a theoretical result. So I'm a number theorist, I work on theoretical questions, and when I work on them, I think that they are connected to some applications, but I'm not an engineer, and I don't intend also to implement them myself. Also, when there is this, actually when I think of this sphere packings in a very wide sense, then there is another word describing this area. It's called actually coding theory, and it includes not only packing of Euclidean pairs, but packing of many different objects in many different spaces. And yeah, so this is a very, again, like a very, very active, very interesting area of research. And it has, again, like two parts. One of them is proving theoretical results, and it's something what is closer to my heart, what I'm working on. And then there is another part about how to apply actually all these packing results to concrete, maybe engineering situations. And it's also very interesting, but it's something farther away from what I am doing.
Do you think the proof of packing spheres in 3 dimensions made with the help of the computer is acceptable?
Sure, maybe it's not for me. It is acceptable. I'm a fan of this proof, and I think also it was accepted eventually by mathematical community. And somehow my personal opinion is I'm not against using computer as a tool, especially if the problem demands it. Maybe what is a danger here is that we just try to completely outsource mathematics, like get very lazy and outsource all thinking to computer. That's not good. And I think it's still worth searching for like short, elegant solutions that can be written in the form of essay and explained to people. But unfortunately, there are many problems that we find interesting or important, and it seems that it's impossible. Of course, it's very difficult to prove that finding nice proof is impossible, but as in this case, it could happen that simpler proof or shorter proof, considerably shorter proof, simply does not exist. Of course, I might be wrong, and maybe somebody will have a great idea, find really elegant, really short argument, but maybe that's not the case. So in this case, I think before we have found this very short, very elegant solution, personally, for me, this is an acceptable solution as well. And I think also, actually, Thomas Hales, he set up like a new standard for mathematical rigor. He did not stop at only proving sphere packing in dimension 3. He also devoted a lot of his work into developing this computer verifiable proofs, so that you write a mathematical proof in the form of, in a certain, I would say, like a computer language, specially developed for writing down mathematical proofs. And then the program, similar to a compilator, which compilates computer programs, it can verify this proof line by line. So maybe same as math teachers are doing when checking homeworks. And then it can say that the proof is correct. And of course, computer, unlike a math teacher or math professor, never gets tired or bored, hopefully. And so then, of course, the proof can be also much longer. So.
Why was the problem solved in dimension 8 and 24? I mean, is there a connection between these two dimensions, or is it random?
Yeah, so this is actually a very interesting question, and unfortunately I don't know answer to it. So here there is certainly a phenomena, something very unusual happens in dimensions 8 and 24, and these ideas of Kohn and Elkis, they work perfectly in dimensions 8 and 24 and don't work, or we could not find other dimensions where they work except for like boring ones. Actually in dimension 1 and dimension 2, same method also works and gives good results. But besides that, we have not found, we're not able to find other instances. And yes, so here there is a still mystery to be solved, like why 8 and 24. And for now, I think I have an answer, but that's not probably not a satisfactory answer. So now it's just, it worked here, so that's why it is kind of connected, but deeper philosophical reason, I don't know, maybe it's still to be discovered.
We have seen that with increasing dimension, the maximum density of the spheres decreases. Is there an explanation for this?
Okay, so there is a proof which says that indeed the density of densest packing will have to decay exponentially. So this is the theorem of Kapatiansky-Levenstein. But it's a rather, I would say, it's a beautiful paper, rather technical. And okay, so like simple word explanation, it's that maybe, so spheres in higher dimensions, they become very, very round. I don't know, but I'm not sure that it's a very like good explanation, but it actually, as we go to higher dimensions, these geometric notions, which I told you that they do generalize nicely, this is true, but this is not exactly true. Because, of course, it means that many things from our everyday experience, as we try to generalize it to very high dimensions, it becomes false. And so these very high dimensions, they, for example, contain, there are many things, there are many paradoxes, or maybe not even paradoxes in the sense that there is something like logical error in there, but in the sense that many things become counterintuitive. And so, for example, multidimensional, think of multidimensional cubes and multidimensional spheres. So in dimension 2 and dimension 3, you know, cubes and spheres, they are almost the same. Like squares and circles, they are a bit similar. Maybe that's why there is this long-standing problem of squaring the circle. Maybe that's why people had this idea. So circle, it's almost like, okay, it's not the same, but somehow similar. So, but we know that with cubes, we can fill the space perfectly. And as we go in higher dimensions, it becomes that the divergence between cubes and spheres becomes bigger, bigger, and bigger. So spheres, they become more and more round. And for example, if you try to, if you look at the cube and try to compute the distance from a center to the cube to its edges, then it becomes longer, longer, and longer. So in dimension 2, it's the same. If you have a, for example, square with side 1, and you try to compute a distance from its center to the edge, then you get 1 divided by square root of 2. And if you do this for cube, then you get bigger number. And if you do it for n-dimensional cube, it actually grows as square root of n, where n is the dimension. So it becomes somehow cubes, they become really like stars. And cubes, they have volume 1. At the same time, if you look at the sphere and try to compute the volume of a sphere, then the volume of a sphere, it will decay, of sphere of radius 1, it will decay very, very fast. It will actually decay faster than any exponential, super exponential decay, something like 1 over n factorial. And so you see that in high dimensions, somehow spheres, they look nothing like bricks or cubes. So they are just this very strange, very, very round shapes. So, and then but for formal proof in mathematics, there are methods like linear programming, or actually there are maybe some older, simpler proofs which say why this density has to decay exponentially. And maybe one thing I want to say that is like also one of the big mysteries is that we know that they decay exponentially, but we don't know what is this exponent, how fast the decay is. And it's also a big open question and related to many deep questions in computer science. So if one of you will be able to solve it, it would be really great.
Thank you.
Have you ever thought that there could be a rule in the succession of maximum densities in the different dimensions so that you can easily predict them?
So, sorry, can you?
So, have you ever thought that there could be a rule in the succession of maximum densities in the different dimension so that you can easily predict them?
I don't think so, because because somehow the packings themselves, they look very different, and also if you look at the plot of somehow what people believe are the densest configurations, then this plot of densities, it looks rather chaotic. It's so maybe there is a rule in a sense, like not a strict rule, but maybe certain tendencies, or like we know that 8 and like dimension is divisible by 8. This gives our configuration certain edge, so to say. But I don't think that here we could find like an easy formula, like I don't know, formula for the sum of squares. You just know that it's like 1 times 1 plus 1 divided by 2, and or no, for the sum from successive numbers. For the sum of squares, you also have a simple formula. But here I don't think you have a simple formula here. And also, I don't think it can be predicted.
Thank you.
So we said that in dimension 2 and 3 the excellent packing is regular. Can we talk about regular packings in dimensions that are bigger? And if so, is it to be expected that in all dimensions the excellent packing will be regular?
So here it's actually a very rather difficult question. So the question is, are the best packings regular? And so this is also a very interesting question, and we don't know answer to it. And I think what is widely believed, so maybe first is, what does it mean regular in this case? Maybe there are different definitions for what we understand as regular. It could be regular, it means that it's periodic, or there is more technical term, so it's periodic, but also with somehow periodic and simplest periodic configuration that can be, which is called the lattice in mathematics. And so here I think the belief is that in very high dimensions, the best sphere packing will not be regular, whatever definition of regularity we give. But that's also a very, very vague statement. So I don't know, I would put my money on chaos, and we would believe that whatever rule we think the packings might follow, probably they would not. And maybe these good rules, they will probably work only in small dimensions. And here my feeling after working for many years with this problem is that whenever nice structure we can think about, it usually gives us advantage for in small dimensions, but then eventually it becomes only like an unnecessary abstraction, and more general packings become denser. But yet another thing is that in big dimensions, studying packings without any structure is just very difficult. So that's why everything I am saying right now, it's somehow hand waving, and we don't have theory here, and we don't have even computer simulations of sufficient quality to confirm what I'm saying.
Why is it more complicated to solve the problem in dimensions other than 1, 2, 3, 8, and 24?
So I think maybe, so maybe one dimensions 1, 2, and 3 are easier than others. Here maybe there is a simple answer, they're smaller. So, but then why 8 and 24? Actually, I don't know why. So it's just, it happened right now that we have a method. It works nicely in dimensions 8 and 24. Never works again. But maybe there is another method which works nicely at 4. Simply we have not discovered it yet. So.
Has the problem of packing spheres ever been studied with spheres of different radius?
Yes, it's also, especially in dimension 3, I think it's quite well studied problem. Here there are theoretical results, there are also different simulations. Also, mathematicians consider packing not only spheres but also objects of other shapes. So there are actually, I've seen once very beautiful, like visually beautiful paper about packing ellipsoids, because ellipsoids then they tend to somehow, sometimes for a certain shape of ellipsoid there is no like regular shape, like periodic one, which would give the optimal solution. But those configurations which come out of simulation, they still have some structure. For example, ellipsoids align with each other, but they cannot perfectly align because their shape does not allow, and this creates some very beautiful geometric pictures. So also there is a quite famous problem about packing of tetrahedra, and it's I'm not sure how true is it, but the legend is that Aristotle thought that the whole space can be perfectly filled with tetrahedron, but he was wrong. And so of course when Aristotle is wrong, then everybody is. People who proved him wrong, of course, are very happy. So and then this opens another question. So if the space cannot be filled with tetrahedra perfectly, but then what is the best packing? And this is all. I think this question is in dimension 3. It's still not solved. There are only some putative configurations which are believed to be optimal. But I think maybe unlike the sphere packing problem, this problem did not receive that much attention. And here it's even possible that not only that there is a proof or solution of the proof of optimality, which we don't know, but it can also happen that there are new configurations which are not known to us yet. So here it's an area where some interesting discoveries are possible.
Was Was finding the magic function a constant logical progression, or did it come to you as an enlightenment, almost by chance?
I don't know, maybe both. So I think there are always moments of enlightenment, but usually to get those moments,
Yeah.
one needs to work quite a lot. So it's
Did it happen that you maybe you had to stop because it was going in a wrong way, and then you maybe found it, or not?
yeah, I think with this kind of research problems that take a lot of time for solving, usually scientists have to explore many different ideas, many different paths. So, and maybe one of the difficult parts of being a scientist is that you are almost always wrong. So at least I'm almost always wrong, and there are actually rare cases when I am right and I'm on the right track. So.
Thank you.
When and how did your passion for mathematics start, and for this problem?
Yes, I think my passion for mathematics started at school. I did not like all the school subjects except for mathematics. No, I'm joking, I'm joking. But mathematics was my favorite subject at school, and yeah, I liked math competitions, like solving difficult questions, and I think in mathematics, one of the very attractive features of mathematics is that here it's like there is no upper limit of how hard things can get. So it's.
And what about your passion for this problem?
Yes, maybe this problem, maybe it was not so much a passion. When I started working on this problem, I already was a grown-up scientist, and yeah, so this is just what scientists do. They have to pick a problem and start working on them, and in some sense, working on this problem, it was maybe also a rational decision. It was just a problem that looked very promising to me, that I thought that maybe solving it will need exactly the kind of knowledge that I already have. And yeah, so that's why I started working on it.
Have you ever been discouraged in the course of your research? Have you ever thought that nothing would come of it? What are the main difficulties you have encountered?
Yeah, I mean, I think all people have some moments when they feel down, and yeah, I mean, and of course, with any new problem, it's not maybe like the one of the features of science is that in science we have to do things that we don't know how to do. And if we don't know how to do them, then we might be on the wrong track, and yeah, things might don't work eventually. So, but I think it's with years, with some experience, there is also an ability to overcome such difficulties, and yeah, you know, like every good dog has its good days.
I would like to ask if it is possible for you make even non-experts like us understand your proof in dimension 8, the basic idea of your proof.
I don't know. I think about this. No, I don't think I can make it much simpler than it is now. But on the other hand, it's also like when you say non-expert, it's very like how much non-expert. So yeah, so maybe the answer to this would be to talk to this particular non-expert and to try to explain. But I imagine that this also will take some time. And, yeah, but unfortunately, I think here there is no really easy cut, and one of the things I like about mathematics is that usually understanding one proof takes. It really requires to study a lot of different theories and to understand a lot of ideas, and that's the beauty of the thing. Maybe I would like to use this as a as a hack to teach a lot of mathematics to that not expert.
What does it mean to be a woman in the field you work in? Is it harder, or there are any prejudices? What did it mean for you to be the second woman to win the Fields medal?
Yes, I think actually I was quite lucky and I did not get discouraged during my career, probably even opposite. Yes, of course, as a woman in mathematics, sometimes it feels a bit lonely because there is not that much other women, and I think it's something what we have to, like, I mean, we as mathematicians, as society, we have to change this. And I think like more gender balanced environment is something what would profit everyone, and women and men who work in this area. At the same time, I mean, I think that I was quite lucky and I did not have bad experience because I am a woman. So.
Thank you.
You have worked both alone and with others. In your opinion, do you work better alone or collaborate with others? How can we develop together a proof? Generally speaking, is the attitude of the scientific community collaborative or competitive?
Yeah, I think that's actually a very good question, and I think the scientific community is actually it's both. It's both competitive. It is very competitive, and at the same time, collaboration is extremely valuable because one thing is because I think it's very good to share ideas and to, as somebody before asked about like where to get inspiration for doing research, and I think the best inspiration is of course discussing research with other people, but it's impossible to have meaningful discussion without disclosing your original ideas or to hearing the original ideas of other people. And yeah, so I think actually both is important, and of course individual work is very important because after all that process of thinking, it happens inside of one person's head, and at the same time, like working alone for a long time, I think it is very difficult, and it's much nicer to have people with whom who at least share the same interests, with whom it's possible to discuss things and maybe even have common goals and common projects.
How does it feel to have won the Fields medal? Have you ever imagined it? How has your private life and working life changed? And was the thrill of having solved the problem bigger, or was the bigger one winning the Fields medal?
Yes, so thank you for the question. And yeah, of course, the medal has changed my life a lot. Now I get much more attention. And yes, I cannot say that it feels bad. It's of course, as there are so very little of, only 4 prizes are given each 4 years. And of course, being one of these 4 people, it's a big honor for me. It's at the same time, I think that maybe the essence of the work of scientists is not like it's not to work for prizes, but to work for the discovery, for finding new knowledge, for so in this sense, so I think somehow maybe making discoveries somehow it's more pleasure than getting prizes, even though getting prizes is also not bad. So.
Thanks so much, all students, and Maryna for all these new problems that she gave us, new hint for research. I know that there are many students who would like to pose other questions, but we have to ask to Maryna how many minutes she can give us, or.
Yes, maybe let's have another 15 minutes. Is it okay?
Okay. Is there somebody who would like to pose some other question? Daniele.
Are you working on other more difficult problems, or you're just like taking your time to do another research about sphere packing?
Yes, so actually I could just continue working as I always did, so work on other problems, and it's not clear, like, are they more difficult, less difficult, who knows, before they are solved, but yes, in your question you put this like alternative, but actually I do work on other problems, but these problems, they're also related to sphere packings and to, I would say, similar geometric questions.
Who else? I know that somebody else wants. Who wants to come?
So, where did you start your work from? I mean, what did you have before you started your research as information?
Yes, so maybe one important thing that I had work of all mathematicians who worked before me, so of course the textbooks, but then also research papers, and in science there is a concept which we call an open science, is that when scientists obtain the result, they write it in the form of a paper, and this paper is published in a scientific journal, and then other scientists are able to read it and to get the ideas. And so when I started working on the sphere packing problem, I of course knew about the research that was done before. Maybe one important, as I already mentioned, important result that I based on was the work of Henry Kohn and Nam Elkis, but yeah, and also my knowledge in other areas of mathematics.
Do you think that there is another problem that you could solve that would be as important as the one you solved?
I don't know, I hope so. Yeah, sometimes also it's not, like when you say, but it's not easy to say which problem is more important. It's, of course, like this problem, certainly the sphere packing problem, got a lot of attention, maybe because it's such a nice geometric problem, everybody can relate to it, and in mathematics there are many theorems which are maybe even more important, but they are much more difficult to explain to non-experts. And yeah, but of course I do hope that at the time that I'm left to work, I will do something important.
Since the Kepler conjecture for size 3 also served to solve the Rubik's 3x3 cube in size 3, could an 8x8 hypercube in size 8 have the same studied properties as a Rubik 3x3 cube in size 3?
This sounds like a homework, right? It's like maybe I need to think about this a little bit. Yeah, but one thing okay, maybe I did not. Okay, I'm not sure about the eight-dimensional Rubik's cube, but this in dimension 8, actually the E8 lattice. It's a very important lattice with a lot of symmetries and a very big group of isomorphisms. I'm not sure that it's exactly related to your question, but yeah, your question, it sounds like homework in a very hard group theory class.
C'era un'altra mano alzata prima? Qualcuno che era dietro? Somebody else? Sì, Greta, vieni.
So as as we already mentioned, you are the second woman to ever win a Fields medal. How does it feel to know you are an inspiration to many other women and girls around the world?
Yeah, a bit scary when you put it that way, but maybe yes, sounds like a lot of weight on my shoulders. But actually, I really hope that in 4 years I will have someone to share this huge responsibility with.
Thank you.
How much time did you spend for understand the dimension 8 and 24?
Just for several years, I think for 2 years before I solved this problem, I really worked on it very focused. It was my main occupation at that time, but I started maybe a bit earlier, a few years before I thought about this problem, but not all the time, maybe occasionally. So after all, few years, I would say.
Okay, so I was just wondering if you ever wanted to work on another mathematic related field other than sphere packing.
On what, sorry?
On another mathematic field, like, no, I don't know, maybe algebra problems, not only sphere packing.
Yeah, but I have worked on in other areas, so. Yeah.
Oh yeah, before I heard that you mainly worked about the sphere packing problem, so I
Yeah, so I say like this geometry optimization area is something I like, but I did my thesis on the theory of modular forms, which is maybe like a more algebraic topic. I worked a little bit on approximation theory, so so I tried different things, and I do like trying different things and finding maybe like connections between different fields of mathematics.
Okay, nice, thanks.
Can we say that the Fields Medal is the best prize you've ever received?
Yes, I don't want to be mean to other prizes, but I guess so, yeah.
You mentioned before that it took you 2 years to come up with a solution to this problem. Since that is a great amount of time, which inevitably must have had some moments in which you thought there might be no solution. How did you know to go on, and how did you know that you could find a solution and that you weren't just wasting your time finding something that had no solution?
Yeah, but I think more or less that's the work of scientists, is to try things, and sometimes they work, sometimes they don't.
You never had a solution in mind, like there was no certainty of having a solution. Like was there a risk of finding out that there was no solution all along?
Yes, of course.
Okay. Thank you.
So we thank you very, very much, Maryna. I think that students can thank you. It is really exciting because we started to talk about you because our colleague Chiara Invernizzi found this problem very interesting, and the nice thing is that, as you said, we can understand a little bit because there is a nice geometric view of the fact, and so she decided to try to explain to classes what is the meaning of your research. And so when she said, maybe I can try to invite her, and so we were so lucky that you came to Milan to go to the university, and so we really thank you so much for coming to our school. We are very grateful for this.
Yeah, so thank you very much. I'm also... Yes, I would like to thank you and your colleagues for organizing this meeting, and to thank students for asking these questions. That were really actually great questions. I answered to many questions during this last few months, and those were among my favorite questions. So thank you. Thank you very much. And, so I also want to wish you good luck in your studies, and in particular in the studies of mathematics. And